Hello, AP Chemistry, and welcome to Chapter 4, Aqueous Solutions. So, obviously there's a lot of assumed knowledge here, right? So as needed, go back and review your stuff from last year if something is fuzzy, or make time to come see me so that we can chat. All right, so first of all, solutions, right? What is a solution? We have a solute and a solvent. Based on the title of this chapter, aqueous reactions. The vast majority of the time for our scenarios, the solvent is going to be ding, 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 water, right? So don't forget water, right? If we think back to last year, looks like this, right, with our two lone pairs, right? Which means that it is tetrahedral bent, right? And because it's tetrahedral bent, that lends a polarity to it, right? In that, we could sort of draw a line across the water molecule, right? Wherein this half of the molecule, right, has a partial positive charge. That's the sign for partial positive. This half of the molecule has a partial negative charge, right? And that has to do with the electronegativities of oxygen compared to hydrogen, right? Not so much the fact that there are lone pairs there, right? Those lone pairs don't make the oxygen negative, right? So it's not these, right? But the fact that the oxygen has a higher electronegativity than hydrogen, right? But anyway, it means that water is polar. That means that water has a directionality to it, which means that, going back to this figure down here, right, ionic compounds tend to dissolve in water because water is ionic and interacts, no, water's not ionic, because water is polar and interacts very well with ionic compounds, right? And so this diagram is very important. This is the kind of question that comes up often on the AP exam, right? In terms of what does it look like at the particle level when an ionic compound dissolves in water, right? So here, for example, if we look at our sodium chloride, right, we have our chloride ions and we have our sodium ions, right? You should be able to tell me which ones are which and why, right, even without the labels. But because sodium ions are positive, right, you'll see that selectively, right, the negative end of water will associate itself with that sodium ion and surround it, right? Going back to what is solvation, this is solvation, right? Where we get that shell of water molecules around it, right? And we get the opposite for chloride, right? So chloride is negative, so you'll see that selectively the hydrogen end will associate itself with the chloride, right? And that's very important. Note that each ion has several water molecules around it, right? That's what it means to be solvated, right? Is that there is a shell of water molecules around it, right? Not one, a shell of water molecules around it, all right? One would be insufficient, say, if you were asked to draw a diagram yourself, okay? Which is different than when other substances, like molecular substances, dissolve in water, right? So when we get a molecular substance to dissolve in water, like we do here, so we have some methanol, right? Where if we think about, in your book, I think there's a figure, right? But we have CH, H, H, and then an O, and then an H, right? So if we think back, right, this part is polar, okay? We could draw that to be bent just like this, right? In that there's an O bonded to an H with two lone pairs, right? In that this oxygen is actually tetrahedral because it's got four things around it, bent because it's got two lone pairs, right? Which means that if I were being more thorough, right, I could actually draw it this way, right? Which means that around this oxygen, right, there is actually a polarity just like there is for water, right? In addition, it is capable of hydrogen bonding, right? So since water and methanol are both polar and both are capable of hydrogen bonding, the molecules can interact with one another, right? Which, going back to last year, that is the key for any one thing dissolving in another, is that there must be a shared intermolecular force so that they can interact, right? And that's what this figure is trying to show you, right? Is that the methanol molecules are interacting with the water molecules via shared intermolecular forces, right? Okay, so then to sort of add a layer of analysis to our solutions, right, we can check conductivity, right? So something can, like pure molecular compounds like water, do not conduct electricity at all, right? And so we'll see what we have here is we have a light bulb, right? And we've got our electrodes that come here, right? And we've got an electrode that comes down here. And this light bulb has a power source, so either batteries or it's plugged into the wall. So power can flow in, right? And power can flow out, but these two parts are not connected, right? So since these two parts down here are not connected, what we need is for that liquid to be able to conduct electricity, right? And the liquid can conduct electricity if it's got free ions, yes? It would be even better to simply say that an aqueous ionic solution conducts electricity. So then, if we think about what that means, pure water, right, does not ionize appreciably, right? It ionizes a tiny bit, which we'll talk more about later. And actually, we alluded to that back in the chapter 14 from last year, right? The auto-ionization of water. But it happens very, very little, right? Which means that for most things, right, a light bulb requires pretty significant energy input, right? We're going to see no conductivity, right? Same thing if we have another molecular compound dissolved in a molecular compound, we end up with no conductivity because molecular compounds are non-electrolytes, where the non implies, right, no dissociation into ions, okay? Versus something like sodium chloride, which is an ionic compound, which is a strong electrolyte, meaning it dissociates completely, right? So I know that when I dissolve 1 mole of NaCl in water, right, I don't actually have 1 mole of sodium chloride. I now have 1 mole of sodium ions and 1 mole of chloride ions, right, in my solution. I don't actually have sodium chloride. Yes, does that make sense, right? In terms of what's actually present. And because we have that abundance of free-flowing ions, we are able to conduct electricity. Yes? All right. Terminology note. This part's really important, so make sure that it makes sense to you from your book, right? But when we say that something is soluble, right, we say that it dissolves, right? We say that the solute and the solvent have a shared force of attraction, right, such that they are able to interact with one another, right? Just because something is soluble does not mean it's a strong electrolyte. Strong electrolyte means that it dissociates into ions and therefore conducts electricity well when it's dissolved in water, yes? Different things, right? Solubility goes to does it dissolve? Electrolyte goes to does it dissociate into ions, right? So not the same thing, okay? And likewise, when we go to insoluble, it does not mean non-electrolyte, right? Which can be confusing, right? Because electrolytes, remember, ionic compounds, right, that dissociate completely, right? That's what an electrolyte is, right? So we have insoluble compounds, or things we consider to be insoluble, right? Like, for example, magnesium hydroxide, right? If we think back to our solubility rules from last year, definitely insoluble, right? And we're going to quantify insoluble in just a moment. But insoluble, right? But if we think about what that means, when we take magnesium hydroxide and add it to water, a tiny, tiny bit of it does dissolve, okay? Because insoluble is like, like a color chart, right? It doesn't mean that none of it dissolves. It just means very little, right? But the very little that does dissolve does dissociate, right? So magnesium hydroxide is insoluble, but a strong electrolyte. Yes, does that make sense? Magnesium hydroxide, insoluble, but it is a strong electrolyte. Yes, the part that dissolves dissociates into ions. Yes. All right, so then moving on to 4.2, let's go ahead and quantify insoluble, right? So when we say insoluble, we just mean that it doesn't dissolve. To put a number on that, I think your book said 0.01 molar, right? So anything less than 0.01 molar. Other books will often define it as 0.1 grams per 100 mils, right? So if less than 0.1 grams per 100 mils dissolves, right, it's considered insoluble. But note that both of those still say some dissolves, right? All right, so then moving along, right, so write the net ionic equation for the precipitation reaction that occurs when aqueous solutions of this and this are mixed. So don't forget, when you're writing net ionics, which become really important this year because they show up all the time, right, what we're doing is really narrowing it down to the things that actually change over the course of the reaction, right? So let's go ahead and practice really quickly. So we have aqueous silver nitrate. Oh, we don't need that. Aqueous silver nitrate. And we have aqueous potassium phosphate. And so obviously this is a double displacement, also known as a metathesis reaction, right? Let's do that last. Ag3, P4. And let's put some states in there. All right. So thinking about solubility rules, right? Oh, we have got a group 1 here. We've got a nitrate here, always soluble, and there's water present because these are aqueous, right? Phosphates are insoluble, except if they're stuck to a group 1, right? So that means this is a solid, right? Now, if we're going to write ourselves a net ionic, obviously you can go through all the steps like we talked about last year, but we could also just think about, do we understand what's happening, right? So if this is aqueous, and ionic, it's dissociated, right? Aqueous, ionic, it's dissociated, okay? Aqueous, ionic, it's dissociated, okay? Here we have a solid composed of these ions, so which means that the net really just is what makes this, right? Because that's the only thing that's different, right? In that the ions are not free floating. So we go back to the reactant side and say, okay, well these ions, so 3Ag plus aqueous, right? Plus that phosphate, so plus that phosphate, aqueous, right? Gives us our Ag3PO4 solid. And that's our net ionic, yeah? Makes sense? All right. This is the end of 4.1 and 4.2. Thank you for listening. Be good, and I will see you soon. Bye.